Herbert.
Yeah, what?
Have you seen the picture of the black hole?
Of course I have.
Yeah, the whole world has seen it, I think.
Yeah.
It's
iconic already.
It's iconic already. Yeah, and that's what we're going to talk about today.
This Houston, contact with a test 1.
Touchdown confirmed.
Would you be so kind as to introduce our guest? Or do you want me to introduce our guest? Because she's special.
I know who she is.
I know who she is too.
Sera Markoff. She's from the University of Amsterdam.
Yes, Sera Markoff.
But you invited her.
Yeah. Oh, I invited her. Yes, I invited you. Professor of Theoretical High Energy Astrophysics at the Anton Pannekoek Institute.
And GRAPPA.
And GRAPPA. What is GRAPPA?
Gravitation and Astroparticle Physics Amsterdam.
All right. Yeah. Oh, it's got its own.
That's the name of your group.
We set up a virtual institute about 5 years ago between physics and astronomy, and it's in astroparticle physics.
That's an international thing.
Well, the whole university is international.
Yeah, okay,
so
well.
it's at the university, so yes.
And you also sat on the Science Council of the Event Horizon Telescope. Of sudden glory and fame of the black hole picture.
Yes.
Yeah. How were the past 3 weeks for you?
Well, it's been a lot more than 3 weeks for us.
Yeah, exactly. Fair point.
The last 3 weeks have been kind of the whirlwind part, right? And I think we were not fully anticipating how much attention. I mean, we expected it to get attention in the physics world and some press, but I think we were really happy to see how much the public was interested. And
this was front page news all around the world.
Except for the Netherlands. Yeah. Well, it was Volkskrant. We got in the Volkskrant, but everything else was, I think, Juventus, Ajax.
Oh, that's true. Juventus, Ajax. Right. That was the same.
Yeah. Same I'm sure it was on the evening TV news.
Yeah, I think we did get it. Here, I'm just joking because there's like, you can see all the front page papers. Somebody made a collection of them, and then they showed the Volkskrant as the only one in the Dutch stand.
Oh, yeah, and that's I complained about that on the show before. That here in Holland, it's like
soccer stars do eclipse everything.
Sports eclipse astronomy all the time. Yeah. But so we're gonna talk today extensively about how you got to that picture and what your role was and black holes in general.
Try not to cough in the mic, sorry.
Yeah, and you have a little bit of a hay fever problem.
Yes, it's the tulips, yeah.
The tulips. The tulips are in full bloom, people. Exactly. But first we're going to go to our stories of the week. I have something that maybe ties into this whole thing.
Well,
so it's as a short introduction. Yeah, I was just, it's just a personal story. I was out in Drenthe, one of the Dutch provinces here, and always surprised and amazed by how many telescopes are out there. The Dwingelo telescope is there. And
LOFAR, Westerbork, Apertief.
Exactly. And I mean, night skies, like glorious night skies, compared to here in Amsterdam, where you just sort of have to find just one single star in the night sky at night. But out there, like beautiful dark skies. And I indeed went to the LOFAR telescope, which is like a really cool, weird telescope.
It doesn't really look like much, does it?
It doesn't look like much at all. Like our GPS suddenly said, like in the middle of a field, like me and my girlfriend, when we were just talking about like how beautiful the nature was out there. And it's just, you have arrived. And it's like, huh? What? What? I see just a bunch of birds and some fields, but indeed it's a collection of antennas. Not only there, but then spread out throughout Europe as well. I think I'm looking at you now, Sera, as well. I believe it's a low frequency telescope, and it's the sort of threads, metal threads. I'm not sure, copper or something. Those are the antennas, but then it's basically the fact that all this data is sent to one central supercomputer in Groningen, city up north, and it sort of creates this sort of like virtual telescope. It's a collection of all these different antennas collected to create one single image. I mean, it's
exactly the same principle as the Event Horizon telescope, and it's not a new principle, right? This is something. I mean, interferometry is the technique of stringing together different telescopes so that you can make a kind of virtual larger telescope. And
interferometry.
Yeah, it's called interferometry.
Interferometry.
So we never say it. We just usually use an acronym. It's the I.
The I thing.
Yeah. Very long baseline interferometry is VLBI.
Yeah. And so that's my story of the week. For Easter I went out and I saw this telescope and I loved it because it had like it had some information there, and there was indeed not that much to see, but then again there was. So I thought it was cool.
We had a real struggle. So I used to be part of it. I've sort of backed out of that now because I focus on other things. But when it opened, we had to come up with something. The Queen came, Beatrix, to the opening, and we had to think of something kind of exciting to do. You know, where you press the button, but it's not like you can make these things turn or do something cool like you see with the big dish arrays. And we made a lot of jokes about what we could do, but in the end, I think what they did was actually passive radar tracked for helicopter. As it came in or showed that on the computer. I'm not sure the security people like that much, actually.
Oh yeah. Yeah, and it's a really cool. It's a nature preserve as well. It's this really odd circle in the middle of nothing.
But you know why you put things in the middle of nothing, right?
Yeah.
Because you're trying to get away from radio interference from cell phones, from other stuff as much as possible.
And cars.
And cars and anything else. There was actually a problematic television they had to get rid of at one point from a farmer. True
you
story.
mean an actual TV set inside a home?
Yeah, so it's almost like an urban legend, but apparently there was a old farmer guy who had a TV, and it was like the old vacuum tube kind, and it was shooting out all sorts of emission, and they had to go try to give him a new TV, and he was very suspicious.
You can have it here.
But there's not that much out there, but there is still something out there. It's like a road runs sort of through it, and there's not cities nearby, but it's a few small towns. Is that not a problem for something like that?
Yeah, I mean, you have to correct for this, right? But the less you have to correct for, the easier it is. So it's always generally you want to try to get away as much as you can. Now, of course, in the Netherlands, you can't get that far away, but that's why most radio telescopes are like in the middle of the desert in Australia or South Africa.
They
or
are so
something.
crazy sensitive.
Yeah.
Yeah, so I was even amazed that a really like densely populated country like the Netherlands still had that many telescopes.
The fact that you can detect a microwave often miles away, it can be
They're
disturbing.
very, very sensitive. And in fact, some of the interference, you could get Danish radio stations as they were bouncing off planes. So there's a lot of passive radar is one way that you can detect things, and it's been used by people in industry as well.
Yeah, and this is low frequency. It's not one of the telescopes that you use.
No, we're at the opposite end. So low frequency is very long waves, and basically it was very hard to do for a long time. And it took supercomputers to be able to do these correlations you were talking about, both at the low end and at the high end of the band, the radio band. Goes for orders of magnitude, decades in frequency. Yeah,
I have a lot of questions about that, but I'll hold out for 1 second. Herbert, you had something.
Yeah, I have a story too.
Big breaking news.
It's called, let me get through the headline, Pepsi drops plans to use orbital billboard.
Oh, no!
Well, I think if they drop the plans, that'll be okay. The story is they were investigating the idea of, launching an orbital billboard bearing their brand name.
Or their logo.
Via a Russian company called Start Rocket.
Okay.
And you can go to their website.
And we could see it at night or something.
Which is startrocket.me.
Okay.
And I would say leave me out of it, but okay. The funny thing is a line that you'll find there. Space has to be beautiful. Get this. With the best brands, our sky will amaze us every night.
Oh,
I mean, come on.
What a horror.
Yeah.
Not to mention probably illegal for, protecting skies for science, right? I mean,
yeah. Could be.
Think about it.
Yeah.
There's not enough inspiring stuff out there. We need Pepsi billboards.
We need some logos.
Yeah, we need some logos. Space has not been branded enough.
Bring in the logos.
Yes, welcome to Coca-Cola
Everything
Venus.
Like that sounds like Blade Runner, right? It's just this kind of...
I'm so happy.
It's an incredible story.
This is we found this under good news.
Did they say why were they forced to put
well,
the idea down?
You won't be surprised. There was some controversy around this. And although nothing that reached me up to this point, but I'll read you another line. The PepsiCo comment: "We can confirm Start Rocket performed an exploratory test for stratosphere advertisements using the Adrenaline Game Changers logo," whatever that may be. Company spokesman told Space News April 15th. This was a one-time event. We have no further plans to test or commercially use this technology at this time.
That's wonderful. Thank you.
They thought better of it. That's the short
Somebody
version.
helped them think better. Yeah.
Yeah, I hope so. So, well, these plans pop up every once in a while, you know.
Oh, yeah.
So,
Yeah,
There was an idea of a fake moon, right? Also, do you remember that one?
yep.
Oh, that's great though. Yeah, a fake moon. That idea I did love.
And
Because
so-
and it's a little more artful than trying to just put a billboard up
but
there.
it's also a bad idea.
Yeah. Orbital display by Start Rockets. A new era of media in your sky tomorrow.
Coming
Please
to your
don't.
sky
Please
tomorrow.
just don't.
I mean, it's a way to guarantee a captive audience, I guess.
Yeah. Maybe also get them interested in astronomy. Would that be impossible?
What do you mean? Oh,
You launch
so if you
something
put
crazy
if you
into
put
the
an
sky.
electronic picture of a star, it's more interesting than a star.
Well, it might attract a bit extra attention. I'm just playing devil's advocate.
Yeah,
here,
I guess
okay?
the problem is that if you have something light in the sky, it's going to interfere with your ability to
Yep.
do actual see the stars, right? Because
That's
you
true.
know, so that's why I guess most people on our side of things would be opposed.
Yeah, I totally agree with you, but somehow I'm trying to think maybe
Mm-hmm.
it could have some positive effect somehow, but then again, maybe it wouldn't.
Let's put the Nike sign on the moon or something like that. Just gigantically.
On the backside.
Yeah. exactly. Well, Sarah, we'll go to your story of the past few years. How long have you worked on the Event Horizon telescope?
Well, I mean, the Event Horizon Telescope as a collaboration is really young. It's only like it's less than a couple of years old as a formal collaboration, but
And were you there from the start?
kind of, yeah. I mean, it depends on what you call the start, and that's where there were many groups around the world who work on black holes, and I've been working on black holes since the beginning of my career, pretty much. I mean, I dabbled in them a bit as an undergrad,
You dabbled in black holes.
and then I went away and did more like kind of some particle physicsy stuff. But then
It's
I came
almost
back.
like you say, I dove into the black hole.
Dove in, came back out.
But I came back out, yeah. And then so I've always been interested in kind of orbiting black holes from my career, and so it's not that big of a field. We all kind of know each other, and then there were different groups interested in this process of building this telescope, and there were separate groups, and then things started to pick up momentum at a certain point, and then there were meetings to discuss coming together, and I was at, I think the first real meeting of that was 2012,
Okay.
where we all came together and said we should maybe do this project as a collaboration and maybe join forces.
And at that moment, you had the idea of using all these different telescopes throughout the world
Yeah.
to create one big sort of virtual telescope the size of
Exactly.
the Earth.
And it was, that was a known thing that, in order to get the precision we knew we would need, we knew it would have to be that way.
And the idea was, can we take a picture of a black hole?
Yeah, can we actually see the event horizon directly? And of course, you don't see the event horizon, you see it being backlit or frontlit, by other material that's around the black hole. So if the black hole was just completely isolated, you wouldn't be able to see it.
Yeah, because
By
if I
definition.
look at the picture,
Exactly, because it's
Yeah.
a black hole.
yeah, if you look at the picture, you see that yellow, orange stuff around
Well, don't
it.
take the
What is-
color too seriously. Color is because radio is something that you see with, it's something you would hear technically, right? We're on the radio now. And so it's not something our eyes see. So to make those images, you translate the frequencies to visual, and you can choose however you want. You can make it blue, you can make it, but because the gas around the black hole is very hot, the decision was made to make it kind of fiery colors, right? To try to give you that feeling.
Yeah.
So that's all artificial.
Yeah, it
Yeah.
could have been pink,
Yeah.
it could have been
But-
yellow.
So what do you
Yeah.
see? There's light there. And
Yes.
so talking
That's
about the
my
event
question.
horizon,
Yeah.
I mean, I understand the black hole because there's a black hole in the middle. And then what's that light around it? What do we
That's
see there?
all the stuff that's basically moving either in orbit or being expelled. We're not sure yet which, very close to the black hole. So the black hole is basically, very massive. It's distorting space-time, and that's what we interpret as a force called gravity. I mean, that's where Einstein got famous, was that one of the reasons, but that he understood that gravity wasn't a force like other forces, but that it was really a byproduct of this space-time curvature. And the more mass you pack into a smaller area, the distortion, we call that compactness, the distortion is bigger. So the black holes are about as compact as you can get. And so space-time becomes very warped, but it's really just, we interpret this as a gravitational pull. So anything nearby, which is by our standards pretty far, but by universe standards pretty close. Nearby stuff will get attracted to the black hole, fall in, it will start to spiral because it has some residual motion. It will interact with itself. It will, sort of like friction. You can also imagine that you'll get heat from this self-interactions. You'll have magnetic fields being generated,
Some
turbulence and
rather
dynamos.
Heavy stirring going on.
Yeah, and the more you get closer to the black hole, you're releasing potential energy, that gravitational potential energy, just like dropping a ball, right? It's not moving when you have your hand up high, but when you drop it, it's moving fast.
Yeah.
That's because you're moving closer to the source of the potential. It's the same with this stuff. It's falling in, it's moving faster. By the time it gets down to the black hole, it's almost at the speed of light. And then it's very hot, very energetic.
So that would generate radio waves, and that ended up in the picture.
Yes.
But suppose you would be near enough to just look at the thing. Would you see anything in visible light?
Yes. Yeah, actually, so the light is being emitted from a lot of the black holes we study. They're basically emitting across the entire electromagnetic spectrum through different processes.
And
Really?
so why?
I thought it was a great question. What if we were actually really close to this black hole? What would we see?
Yeah, you would see probably something quite similar. You would see, first of all, you have to remember what we're seeing now is through the eyes of a telescope. That isn't a perfect thing, right? So if we see something that looks a bit like a blurry donut, right?
Yeah, I saw complaints on Twitter that it was blurry.
It wasn't good enough for them.
Yeah, it wasn't good enough.
Well, I'm sorry if our planet were only bigger. Our planet's clearly not big enough.
Yeah, next time we'll do it from Jupiter or something.
But why then use radio waves to look at it? Is that just because the light doesn't reach us at all?
No, it's because of the technique. We simply cannot do this. This combining of telescopes to make a virtual telescope called interferometry.
Yeah.
We can't do it over large distances except in this radio to millimeter band. That just has to do with the technique. So this interferometry, this combining of signals, for instance, you could do this in the optical and the infrared. They do this at the Very Large Telescope in Chile, VLTI.
Yeah.
There's CHARA, there's a couple other arrays, and these things cannot be very far apart because you can't correct. Basically, you have to keep in real time correcting for the signal. The atmosphere is very variable. If you go to higher frequencies like the optical infrared compared to radio, it's varying so fast. You just don't have the ability at the moment technologically to correct and combine these signals. So this is something where we knew how to do this in the radio centimeter bands. Then LOFAR was the one that path found there's a few instruments, but one of the main ones that has path found the lower frequencies and how to combine signals. Now we had to push to what's called millimeter, which is moving our way towards the optical, but not there yet.
Towards the optical. So it's
higher
still
energy.
Still in the lower end, but it's
we're still in the radio band, but it's basically around a millimeter instead of a centimeter.
So you're moving your way up the spectrum. So maybe someday you would get to visible light.
Yeah, I mean, I suppose again, it's a matter of having it would be huge data rates. It would be very difficult, but in principle, it's possible.
So to understand it correctly, so first you had that meeting. You were at that meeting. You said we need to do this. Then you knew the only way we can do this is radio waves. And then the next step is, where do we find these telescopes? Who can join in?
So to be honest, I mean, the meeting was in 2012, and there had already been prototype experiments of millimeter or sub-millimeters, where you really want to go a little bit higher. There had already been prototype experiments built with a couple telescopes and showed already in 2008. There were papers in Nature by Shep Dulman, who's the project director now for the EHT. He actually had worked on this and shown that it was possible to do this with very long baselines. And there were already observations of the two black holes we looked at. But the point was that was done by a smaller group of people. And once you had that proof of concept, then it was feasible. I think you have to show the funding agencies and the governments and all the people who are involved who own these telescopes. Yes, we can do this. Help us, right? But then you need a lot of money. You need a lot of support and resources. So that's where it sort of builds up.
Yeah. How many organizations did you have to contact?
I mean, well, it depends what you mean. For funding agencies, we had quite a lot.
More for telescopes. How many telescopes did you need to point?
Well, all the ones that we used. So we had 8 major facilities basically that we had to, and they each were owned by usually a kind of a public foundation. So similar to the, in the Netherlands, right, we have the Astron Institute, and they're running LOFAR, at least the Netherlands part. Then you have international institutes that run each of their own ones. And a lot of these were owned by national institutes. And we have, the way it works to use telescopes in general is that usually about once a year, sometimes twice a year, there's a competition basically where you propose and you say, I would like to use your telescope. Here's a form and here's what I want to do.
Yeah.
Here's why it's feasible. And then there's a committee of scientists who peer review it. And then usually the more competitive a telescope is, the harder it is to get time.
Oh, yeah.
Like Hubble. This is how Hubble works, right?
Yeah. Yeah. And so you filed this. Do you remember when you filed it all?
Well, oh gosh, I mean, you're getting into some of the earlier politics. I think the biggest issue was we needed to get ALMA, which is it was a relatively new millimeter array. So it on its own is the best millimeter array that does interferometry, but it's smaller and it's built in the Paranal in Chile, like very high up in the mountains. And it was built not to do this. It's just a telescope. It has its own design to do a lot of things with astrochemistry, star formation, study other kinds of black holes. It's a workhorse, one of the largest workhorses in the world, and it's a big international project. We needed to get that to operate as one single telescope, which means you have to phase together all these different telescopes that are there into one, and that was a bit of a political thing, because not only almost run by a consortium of many countries, it had to be decided that the will was there, then the money had to be there to do this and the technology. So that took some time.
Yeah. And it's a schedule thing also, I guess, because you need all these telescopes at the same time.
Yeah, exactly. And so it's this complicated dance that from the prototype, we knew it was possible, but we knew that we needed ALMA phased together as really the kind of ring that binds them all, right? I mean, it's the thing in the center, and it helps stabilize all the others. And only once we knew that ALMA could join us was it possible to do the full run, and we needed that to happen, and that was why it happened only in 2017. It took that long from early days. People had thought about this even back in the 90s. The first prototype of Event Horizon Telescope, as we think of it now, was with 3 telescopes in 2008. Then it took 2012 was kind of people coming together, already trying to work with ALMA to get this phased up. And then by 2017, we had that and these other instruments, and we had the time proposed. But we had to get
They all
ALMA.
had it at the same time?
Yeah,
They all had to look at the same time.
So we had to all look at the same time across the array. It's not strictly true. In some case, we use a subset for some north. You can't see from planet Earth. You can't see the same sky all the time at every part, right? I mean,
The Earth is not flat.
it's not flat.
No.
Although
some people think otherwise.
Good thinking, guys.
but if it is flat, I guess you wouldn't be able to see the other side. I don't know how that works, but so we have some sources like M87, for instance, that didn't use the South Pole telescope because the South Pole is too far south to see M87, which is more in the northern part of the sky. And then similarly, we have, when we look at Sagittarius A star, South Pole telescope becomes very important. But ALMA's always there in the middle seeing, these. So that's why it's very important, whatever source you look at.
Yeah.
And so again, how many telescopes did you use?
Well, I mean, so again, it depends on how you define a telescope. There's a
Yeah,
myriad if
you
you
define
put
it
them
for me.
inside.
Yeah.
I mean, there's sort of the 8 major facilities that were spread out across the world.
Eight major facilities,
Yeah.
all with a sometimes array of different instruments. Trying
Some
to,
are single dish, some were an array, and then we had to get them to talk to each other and
Well,
and
it
have
means
the
writing
same.
a lot of software, I guess.
Yeah, so in fact, similar to LOFAR, which you mentioned, these are like a lot of. We can almost say they're kind of half software.
Yeah.
The software is critically important.
Yeah, and I heard a story about a whole bunch of hard drives having to be flown from A to B. What was that story all about?
Well, so basically, the amount of data that you take is something like 6 petabytes.
6 petabytes.
Yeah,
So
so
6,000 terabytes.
Exactly.
Yeah.
So if you imagine thousands of these hard drives that you would have, that's a lot of volume. And so these literally, there's no way we currently have to pass this data using, a optical fiber or something like that. So they literally have to be packed up in crates from the telescopes and shipped to the correlators, where you have these supercomputers, one at MIT Haystack, one at Max Planck Institute for Radio Astronomy in Bonn. And these are 2 big hubs for radio astronomy.
And that's so. And then you feed these hard drives. You feed it into a supercomputer.
More or less, yeah. So the point is, right, that what you need to do is you need to have the telescopes are looking in real time, but then later you pack up all the data and you have to then ship it back and then put all this data back together in real time. So the way that works is you have to time tag the data. And
How long were they looking for?
Well, so we had. Yeah, that's another question. Because we basically were given a window of around 10 days. But then within that window, I think in 2017, we had 5 or 6 nights. And then per night, per source, I mean, we were looking for something like 17 hours on one source, maybe 20 on the other, but in total over the week. And then what we did was there was a group that came up with the scheduling, and they were sort of the gods of scheduling, right? I mean, they would sit and juggle all this, and we started calling it Sudoku because it was like this complicated thing. And they made pre-selected tracks on the different sources, knowing, at a given time, which sources were visible, which sources were our priorities and which were less. Because we were looking not just at the 2 that we could see the event horizon, but several other sources that are either used to calibrate those sources, but they're also interesting sources as well. And these are all black holes, but some you can't see the horizon.
Okay.
Other objects in the sky.
So
they're called active galactic nuclei. Yeah.
Active
galactic nuclei. That's what we call any supermassive black hole in the center of a galaxy that's doing something interesting.
And which one did you pick? Which one did you really want to take the picture of?
Well, the only 2 that we think we can see the horizon of all the black holes in the universe right now are M87, the one that we just published, and then the one in the center of our galaxy, Sagittarius A star. But we also looked at about 7, I think, 6 or 7 other ones. Some were science targets for other reasons, just because it's still interesting to see that close in. We're really interested in these things called jets, which are being expelled basically at the speed of light, huge structures that alter their even host galaxy. And we've never been able to see the bottom of these things, so we wanted to be able to try to see as close as we could.
What do you mean,
the
jets? Bottom of a black hole?
No, the bottom of the jets.
Jets?
Basically, these huge structures, we can see them extending beyond the galaxies in some case. And we think they're very important in cosmology. They actually play a role in impacting large-scale structure. And it's this whole thing we call black hole feedback. It's basically the long arm of the black hole. And how these things are launched. That's actually my field. That's what I'm interested in.
Wow, there's so much in here. We need to unpack all of this. So listeners...
there's a lot.
Yeah, okay. So
can I ask...
Of course.
Why?
I'm going to write a couple of things down so we don't forget.
Yeah, all right. You're telling us that in all of the universe there are 2 black holes that were sort of fit to be photographed in this way.
Yeah, at the moment.
Why just 2?
Well, it just has to do with there are black holes everywhere.
Yeah.
But the size that a black hole's event horizon is going to fit on the sky is basically dependent on their mass and their distance. It's basically the ratio of their mass over
bigger
distance.
mass means bigger...
Yeah, bigger event horizon.
Bigger hole, yeah.
Which means bigger size.
Sure.
And then distance means it's going to, get smaller, right?
Yeah.
So if you just think about a light bulb or...
So they need to be either big enough or close enough.
Exactly.
Okay. Yeah.
And so M87 is a monster black hole. It's 6.5 billion times the mass of our sun. And it's about 55 million light years away.
Yeah.
And it turns out that it's so big that it looks on the sky almost the same as the black hole in the center of our galaxy, which
That's
is
how big it is.
Yeah, which is about 1,000, 1,500 times smaller.
So all other black holes
closer.
are either too small or too far away.
Yeah, I mean, so there's a gazillion black holes out there, right? But having one that's big enough, close enough, and then of course we're limited by the size of our array. So if we want, of course, people are thinking about this. Then the next step is to get off planet, start doing space VLBI, where
Put
you
one
actually
on the moon or something.
Yeah, the moon, or even the moon might be too far. Actually, orbit might be better. And so there's a lot of discussion about what you could do.
And then you get more candidates.
Yeah, and then you could have more candidates.
Yeah. So I want.
And this is going to happen.
The funding agencies and this would be the idea would be nice to do that, but there's no concrete plan. People are starting to think this could be a fun thing to do.
To have a telescope out in space, maybe that's huge.
Well, I mean, LISA, which is the next, this is a funded mission to look for gravitational waves. That's interferometry. I mean, the gravitational wave detector is also an interferometer. It's this, and so that is a space interferometer. And in fact, NASA had plans that were already in what's called phase A, I think, the first level of decision making, and already approved prototype called Space Interferometry Mission, SIM.
Yeah.
And then in the vagaries of, how things shift in politics and priorities, there was a funding shortfall in the US, and NASA made the decision to cut it.
Yeah.
But
would love to talk more about the jets and what we all learned. I think first how we got to the picture, and then we'll just talk black hole, some more black hole.
Sure.
So you said there were 6 sort of, how did you call them? More like calibration points that you were also looking at. So you had, I believe, a couple of nights that you were staring up, 6
Right.
petabytes of data.
So do you want to? Sorry, I'm not sure. 6. You're talking about the number of nights we looked, or the number
Yeah,
of sources?
but I'm just trying to get like a comprehensive picture of like how much effort, because it's insane the amount of effort that went into this, and how big of a
so it's
project this
basically
was.
There was a lot that went into this, because in order to take a good image, you need to have good telescope conditions across the array, and that can mean a lot of different things. That means the telescopes have to be working well. Sometimes you can get animals in them, you can get snow or ice, things happen. Things just don't work sometimes, right? This is technology.
A mouse in the freaking telescope.
Yeah. Well, LOFAR, they had problems with, I think, was it mice or sheep? Something was chewing on the wires at some point.
I
this
forgot
is
what
different
it
than-
was.
And
Yeah.
in
Always
space,
squirrels.
you have problems with space. There's things happen, right? It's just technology. So you have technology issues that you have to make sure everything's checked. So it's just like a NASA launch. Every night we had to, I should say ESO, ESA, I'm sitting in Europe, but as a launch, you have to, so we would sit, there was a kind of a control group, and we had weather reports on all the stations. And then part of my role in the project was to help coordinate, on top of that mess, also multi-wavelength facilities, because in fact these black holes are emitting in other wave bands. And so we simultaneously tried to look also with space satellites in the X-ray, with gamma ray telescopes, with infrared optical. We tried to do it all.
Wow.
Other radio telescopes even, and other frequencies, and we tried to get everything to line up with the Sudoku. So what would happen would be that the scheduling people had come up with these tracks of how the telescope would work, sort of possible tracks where it would be like, okay, we're going to trigger this track, because it's very hard to, on the fly, set up all this equipment. So in a way, it was like presets that you would, code in your radio in the old days and like press a button and it would do something. We had presets for the telescope. And then on any given night, we would look at all the weather, look at the stations, try to decide if we had really good observation conditions. Well, then we wanted to go for the money shots, as we said. So then we would choose to go for our primary targets. But if we also had to burn through the time that we had, because we only had 10 days.
Yeah.
So there was always this risk, if you didn't trigger one night, that you would lose, maybe it never got better and you lost it. So there was a real harrowing decision every night. It was really stressful, actually. I'm glad I wasn't in charge.
Where were you physically?
I was in the Netherlands, and the sort of group that was deciding this was sitting in SAO in Boston, in Cambridge, Boston, and then but then there were people also like me, coming in sometimes. I wasn't there for every time, but sometimes I tuned in because of the multi-wavelength was also an influencing factor. So you had all these factors of like, do we have observations lined up with X-ray telescopes? It's very hard to get. Well, you might want to prefer to look when you have it than not. And so we had to weigh all these decisions. But in 2017, we just had excellent observing conditions. We had great data. We observed straight. Nobody thought it would be that easy. And in fact, it exhausted the people who were on site at the telescope, because also there was the team members who were on the sites and they had to operate the telescopes. And they didn't get any sleep because it was just hours of constant observing night after night, because we thought we'd get breaks with bad weather.
Yeah.
That's what normally happens.
It all went sort of perfectly.
It just went really crazy perfect.
Wow.
And that's so.
And so the panel gave the go, and everybody started listening.
So we really, in the first few days, we did our observations already of M87 and Sagittae. We got the things that we were the most worried about. Then we did some swings onto these other objects. And then during the night, you also look at them sometimes in between as a calibrator. So you would look at that between sources, or, it just has to do with positioning on the sky. But this isn't a mystery. I mean, this is something we we know where these things are and put that all together. And then towards the end, we had a little, then we went back and looked at things again. And we tried to make sure we paved the time.
Yeah. And did you know you had it at the moment?
No, of course not. I mean,
No?
we had data. We
had
took
data,
we
yeah.
took data, but we didn't know till very long afterwards.
It's not like on a digital camera where it's
No.
just like an instant preview.
Yeah, I mean, you couldn't just look at it and say, we got this. I mean, basically, you just had petabytes of data that you were going to have to sort through and sift through and see if
Yeah.
correlate it and see if it actually really worked.
Wow.
How much time did that take to develop the picture?
Well, I mean, just to give you so then there was a very strict process of, internal teams doing the calibration and the imaging, and there were independent teams that worked separately with different algorithms because you really want to be careful. And the date we sort of consider really that the collaboration got to see, everybody got to see was July 2018.
Okay.
So it
Of
was
that year.
over a year later
Oh, okay.
Wow.
Over
that
a
we
year
got to
later.
actually see the first image.
That's really crazy. I mean, at a time when you're used to doing click-clack and you have the picture.
Yeah, it's kind of delayed gratification.
Incredible.
Exactly.
It's much more time than I thought it would be.
Yeah, but you have to remember this was a new technology.
Yeah, sure.
I mean, it just takes time. And for instance, we had to ship all this stuff, and that takes time. And then you had to deal with this correlation and all the techniques and different teams doing things. It was just very large amount of effort.
Yeah.
Yeah.
I saw
okay.
I saw a TED talk by Katie Bouwman.
Yeah, of course. And
Yeah.
she's one of the people working on the algorithms for the
On the
imaging.
algorithm, right?
Uh-huh.
Yeah. One of the people who then had an algorithm. She didn't have a background in astronomy, but in imaging.
Yeah, 'cause she was a computer. She's actually just starting a faculty job at Caltech in computer science.
Yeah, computer science. And in that talk from, I think, 2 years ago.
That was from her PhD thesis.
From a
I think.
PhD
Yeah.
thesis. I must say that the pictures that she showed looked eerily similar to the
final thing.
The final thing.
Yeah, well, that's because, I mean, we were, it wasn't like a total mystery what we were expecting from the theoretical side.
Yeah.
As physicists and as astronomers, we have an idea, a pretty good idea, actually, of what's happening around black holes and how they work roughly. So we were using those simulations. Like, that's part of what I do in my group as well, is we take a basically computer and we put a black hole in it with warp space time and we throw stuff on it and then we, see, and then you try to make fake images from these simulations. And so we had a ton of those things in the bank. And then we were running the image processing on that before we actually had access to the real data to practice.
Yeah. This is totally clear, but I'm going to tell you, Thijs, what was eerie to me, at least at the time, when this photo had appeared in the press, I went on the internet and started looking around, and I found this video from a channel called Veritasium. You know it,
yeah.
Sarah? But you, Thijs, do.
Yeah. I love that channel.
This guy had an explanation of, and the video appeared before the press conference and everything, so he didn't know the actual picture.
Yeah.
But he set up an explanation and blah 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 blah.
Yeah.
And in the end of his video, he said, "So the picture that's going to be published soon will probably look a lot like this." And there was an eerie similarity between what I had in the meantime seen in the press and what he predicted that would be there.
Yeah.
How is that possible?
Well,
Well,
just because the theory said it would look like
Well, I was
that.
going to say, I think it's a good
And the
sign that
simulations and
we're,
everything.
we know what we're doing more or less on the physics side. There's a lot of unanswered questions, which is what we still need to understand. Part of what what's interesting is a lot of our uncertainties about the physics have to do with larger scale structures, how this donutty thing, which is basically what's happening very close to the event horizon, connects to the larger scales. And the physics of that, that's not what we're looking at, actually. So by looking with this precision at this high frequency, we're picking out basically the scale that is the event horizon or very close to the event horizon. And that's completely dominated by light bending effects from gravity. So, basically gravitational lensing. So in a way, what that means is that it's almost robust. We made 60,000 fake images, not fake, but, model images based on our simulations. We ran tons of different simulations with different, geometries and different gas physics. And that's where a lot of the stuff that the public would probably not find that interesting, but we are very interested in. All that stuff was put in. And the images more or less are robust to that because they're being dominated by the wrapping around of space-time.
Yeah.
So where I think it's going to become very interesting will be the future as we start to, first of all, we have a lot more information to extract from this data. Polarization gives you information about the orientation of magnetic fields. That's extremely constraining for us to understand the geometry. Variability, so going in, now we have data from 2018 for the same black hole. We have to look at it again and again. We're trying to get it again for 2020.
Oh, so you will be able to make an animation.
Yeah,
eventually.
so we want to make movies. We want to understand the orientations and so on.
Yeah.
Different black holes.
Event Horizon, the movie.
Yeah, the movie.
The movie.
Right.
Yeah.
A frame a year. Yeah. And
frame a
so what will, I mean, it's always such a horrible question, but what will this teach us about the black holes? Like, or is this a method that you want to use to just step by step get
well,
to
it's
know
a lot
them
of things
better?
to a lot of different people, right? So I think if you ask a person who's interested in specifically in general relativity, right? Everything that we see, those models we used assumed, general relativity. And we found something that seems to look pretty much exactly like you would expect if Einstein were correct. And the mass of the black hole that you could directly get from the size, basically, turns out to be exactly on top of an independent measurement using stellar motion. So that's very reassuring, right? There doesn't seem to be something weird going on. And then LIGO and the gravitational waves basically also seem to support general relativity for small black holes. So from a theory point of view, as far as we can tell, Einstein had it right. There's just no reason to think he was wrong so far.
Yeah, you're suddenly confirming and verifying all these things that he said 100 years ago.
Exactly. And so that's pretty interesting. But then, of course, if we could...
Pretty interesting.
Yeah. But, I mean, there's a lot of work you can do. And so suppose we can make our images sharper. Suppose we can increase the sensitivity in various ways by adding more telescopes, which is the next step. We'll have 3 more telescopes in 2020. We had more telescopes added in 2018. Then you might be able to eventually get a sharper image of the ring, and the shape of that ring tells you about the shape of space-time, and there might be deviations. That's something that people would like to see. This starts to get into why, people who are interested in quantum gravity have a lot of ideas about black holes and what black holes are. And it's been difficult to connect the real black holes to these mathematical black holes, but we're getting to the point where maybe we could start to connect them. So that's
Awesome.
That's one side of it. Then there's people like me who I'm more of a pragmatic person. Like, I love the GR weird space-time stuff, of course, but I'm also interested in the fact that black holes actually wreak a lot of havoc in the universe. I mean, they're really destructive forces, and they're interesting. And
Can you give a few examples about their destructiveness?
well, so basically, we understand a lot about the initial conditions of the universe now, the Big Bang, right? We can look at the cosmic microwave background, which is a photograph, effectively, of the time where light and matter kind of separated. And then from that moment on, stuff was able to collapse, and that became the beginnings of the structure we see today, of the largest bound structures, which are galaxies and clusters of galaxies. And so that pattern, in effect, you could put that into a supercomputer, and that's what people do. And they run it forward with all the fancy stuff, and then they basically make a model universe. And I don't know if you've ever seen some of these. You can find them online. You can even fly through them. They're pretty cool. And they take, a gazillion hours on the best supercomputers in the world, and they make these models. Well, people started to realize, even about 15, 20 years ago, that the universe they generated, if they ran the thing forward in time, didn't match our data, that you get this filamentary web structure of galaxies and clusters of galaxies, and we were getting too many massive galaxies. And
So it was like we're not getting our own universe back.
yeah, well, exactly. I mean, something was obviously wrong in the model. And the thing is, the only process that we can imagine, or that we know of, that could affect structure on this largest scales, and actually what was happening is we were over predicting the large scale structure, had to be black holes because of these jets that I was talking about they launched. So somehow, and we're talking about scales that are hundreds of millions of times bigger than the region that launches them. So they're just enormous.
These jets. Hundreds of millions of times larger.
I mean, and if you look online at some of the talks I gave, like for the press conference or also at South by Southwest and things, I give some pictures of this. You can see them. But we see these things, and they have to be launched from black holes. We don't know any other process that can give you the energy.
What's in this jet?
It's basically just very hot plasma particles. We're not entirely sure of the balance between those particles and magnetic fields. So that's one of the questions. We actually don't really understand how they can be squeezed. You know, the stuff is being sprayed out from the black hole nearly the speed of light. And it's like a fire hose that goes out through the galaxy, beyond the galaxy, stays completely intact. And when it gets out there, it just dumps a bunch of energy and messes with the environment, and it heats up the gas and prevents star formation. That's one of the things it can do.
It prevents it.
Yeah, because stars can only form when gas is almost as cold as space. So when you heat it up by dumping all this energy, then, and it's not just the jets. I mean, that's a simple story, but the black hole can also give off winds. The formation of the black holes can also generate turbulence and heat. There's a lot of the growth of black holes throughout cosmic history has been linked to the growth of structure. And there's this back and forth that we want to understand. So, I mean, that gets way... It's not really what the public normally thinks about with the black holes, but that's what I'm interested in them for.
Yeah, black hole is a black hole. It's something that nothing leaves from it. It eats everything. But you're saying that there's actually a lot of energy going around it.
Yeah, exactly.
And these jets.
And they create. They're very visible. They're very important. We think that these are also the sites of the highest energy cosmic rays. We see these extremely high energy particles from space, and we think that these are the sort of CERNs of outer space, that are accelerating these things.
Particle accelerator, yeah.
Exactly.
Yeah.
Is there a jet, basically, how do you call it, shooting our way? Is there a jet that we can look straight into?
Yeah, there are many. When you look at distant other galaxies, there's just, they're randomly oriented. So there are some that are pointed directly our way.
Shooting through us right now.
Yeah, but I mean, we don't, there's far enough away that it's, I mean, what is that? There's 300 neutrinos going through your thumb at any given time or something, right?
But so are these coming from black holes then? Or
some of them, yes, the high energy ones.
Yeah. When you're saying it's shooting out particles, I'm always wondering what kind of particles then? What sort of thing comes out of a black hole?
Well, I mean, so some of the particles are, imagine that these are just dredging up material that's falling in. So it's whatever star stuff and gas, and it's going to be a representation of the gas that it has available to suck up that gets shot out. And a lot of it will be, some particles may be created in the extreme magnetic field. So you'll have electron-positron pairs. Then particles can collide. Two energetic protons or an energetic proton and a photon can collide, and they'll make other particles like pions, and then they'll make other particles. So one of the things you've maybe heard this buzzword now, multi-messenger astronomy, and I don't know, that's the idea that when the gravitational wave source that was seen in 2017, the binary neutron star merger, that was where everything came together.
It was the first ever official gravitational wave that was...
that had light and and so basically these jets were also launched in that system. So jets tend to come out when you have compact objects, strong gravity, magnetic fields. And so at the exact same moment, basically, as the gravitational waves were emitted, gamma rays were emitted. And then a little bit later, you had radio and optical and infrared and all this other stuff came out. And studying all that together gives you a picture of the physics. And that's why we tried to do the same thing with EHT, that we try to combine
the Event Horizon
Telescope with these other things. Because at the same time we're seeing the root of the system, we also want to study the jets with the other telescopes and look at maybe stuff coming out. Yeah. The black hole in our galaxies flares about once a day. On average, and
it flares.
And we see these flares in the X-rays and in the infrared. So,
and does it flare does it flare something outside of itself, or does it come from inside the black hole?
We don't know, because with X-rays we don't have the ability to look like with the Event Horizon Telescope. All we see is that the flux of light coming out jumps, and it sometimes jumps a little bit, and sometimes it jumps by a factor of 1,000.
And nothing should be coming out of it.
Well, it's not the black hole. Just keep in mind, it's not that the black hole is that you're breaking the event horizon. It's stuff around the black hole.
Yeah.
Some process is basically making these flares. Something like solar flares, but we think it is kind of like solar flares, like some magnetized stuff, maybe magnetic reconnection, but we don't really understand it. And the other interferometer I mentioned, the very large telescope, in the VLTI interferometry, so they take the VLT and they put it into this interferometry mode in Chile. Mm-hmm. They actually have an instrument called Gravity. You may have heard about that last year. Big news as well, because they can basically see a little blob of stuff orbiting around the black hole. And we're trying to now observe together with them in 2020 and to see if we can resolve maybe the structures that are, in real time moving around the black hole and making these flares. So it's very cool.
This is like looking for exoplanets on a different
Yeah.
scale.
I mean, it's exactly.
You're going to see so much more detail than you used to. It's incredible.
It's really, if you had told me, 20 years ago that we could do this, I would have not believed it.
Neither would I.
Yeah, because and that's what's so mind blowing about it, because we all think that a black hole was sort of like a nothing, a pit in which things fall, and now it seems to be way more alive than we thought it were.
Well, it's all gravity, right? It's just the fact that it's a sinkhole, so it doesn't even, for the sake of this stuff, a lot of it could just be a really heavy rock, right? But it's just the fact that it's an extremely compact rock.
Yeah.
Yeah.
Because these jets are shooting out, is it also possible that a black hole will die out and become something else? That it loses too much energy?
It would take probably more. I mean, it would take a really long time. It's sort of, similar to Hawking process. You can extract energy. You're not actually extracting so much the mass energy of the black hole. With these jets, you're extracting energy from the stuff that falls into the black hole, and maybe some of the rotational energy of the black hole is being tapped as well. So you could spin the black hole down by doing this jets, but you're not going to probably make the black hole evaporate at this stage. Yeah,
it won't evaporate or turn into something else.
It would, maybe it will. If you think about like billions and billions and billions of years in the future.
Billions and billions.
Because these jets are not from material from inside the black hole. They're from material.
Yeah, I mean, they're a mix of stuff. Nothing comes from inside the black hole.
That's right. Yeah.
But
well, you're doing air quotes. People at home don't see it. But
yeah, sorry. Air quote.
Nothing comes from inside the black hole, or something actually does come
from
from
the astrophysics point of view, no. But what's happening is the magnetic fields that don't come from the black hole but are drawn in and created by the stuff falling in, these magnetic fields get amplified, similar to the dynamo that happens in our sun. There's turbulence and basically you end up going from weak magnetic fields to very strong magnetic fields. They get stretched out as they move in closer to the black hole because they're pulled together with the stuff that's being flung out. It's just centrifugal forces. It's the same thing like spinning around, everything's moving, things fly out. The magnetic fields will go with it, but then there's so much pressure of stuff also falling in, it will press the magnetic fields up against the surface. This sounds weird, but black holes have a surface in general relativity when they're spinning, and it's called an ergosphere. And this
learning so much today.
Yeah.
And
that is different from the event horizon.
Yeah, it's a bit outside the event horizon, but just outside the event horizon. And what's possible is that you can extract energy from the black hole via this process. So you can think that effectively these magnetic fields will hit this moving surface, which is rotating. Then the magnetic fields, if you think of it just like a wire being stuck onto a ball that you're twisting, it will coil that wire up. Yeah. And that's exactly what happens to the magnetic fields. Well, if you have a coiled wire, it's got a force. Magnetic fields have a force, and they want to not be near each other. Magnetic fields want to be straight. So you have a coil, it's like a spring, it wants to stretch out. And in some sense you could think that the black hole becomes an engine or a battery with a coil. There's currents generated, and then the whole thing wants to kind of move outward. So to some extent, that's a simpler way to discuss, that we have these jets. It's of course, a little more tricky than that, but that's one of the main processes. So we see that the jets are probably a mix of magnetic fields from the outside accretion flow and plus a little bonus that's coming from tapping the spin of the black hole itself via the ergosphere.
Okay.
When I was reading up in preparation for this episode, I hit upon a figure somewhere that for every quantity of matter that disappears into a black hole, 99 times as much is spit out from the material of the disk around the black hole. Is that true?
Well, that number varies, right? It's going to depend a lot on the stuff and on the magnetic fields.
Okay, what kind of?
Yeah, because you can have the magnetic fields really control a lot of the dynamics. And in fact, they have a force and they can push material out. And also light can push material out. This is what gets kind of crazy when I talk about feedback, and that gets into complications, but you can't indefinitely feed a black hole. So if you just keep dumping things onto the black hole, it will get more and more bright. The material will get hotter and brighter and more light will come out. But light itself has a force. And eventually the force of that light will start to push back on the
Oh,
accretion
yeah.
flow, or the magnetic fields will
The solar
stop.
sail effect.
Yeah, exactly.
Yeah.
And so what can happen is that's part of what we call this feedback cycle. So what we think is that from the early stage of the universe, black holes, there were these proto black holes that formed early on that became their first black holes. That's actually a big field. We don't fully understand how the first black holes formed. But they formed in the center of their galaxies that are all forming around at the same time. Then they get fed very fast in the early universe. They grow immensely. But at the same time, they're emitting a lot of light and stuff, which has the effect of sort of stopping the growth of their galaxy. But then they also stop their own feeding process. So then things die down again for a while. Then once the black hole dies down, the light goes away, the pressure goes away, the magnetic fields go away, and then stuff starts to fall in again, and the whole thing. And we see, we can see this.
Yeah.
So we see not only the jets, but we can see, for instance, huge cavities that they carve out in their surroundings that basically seem to be bubbles of activity every 100 million years.
Oh, really? Oh, yeah.
yeah.
Okay, because they
Yeah,
sort
they're
of
sort of
breathe
burping,
almost.
yeah,
exactly. They
stuff
burp
out,
out.
yeah.
Wow.
A crazy amount of stuff happening.
Yeah. And this is the same for supermassive black holes and regular black holes?
So what do you call regular stellar
I don't
mass?
know. You tell me. Just stellar
Run of the
mass.
middle
Just
black
small
holes.
ones.
Yeah, so this is another very interesting area. It's another place that I do a lot of research on. So the space-time effects of a black hole general relativity should be the same, right? So the only difference would be, between black holes would be their mass or their spin, according to astrophysics. But the stuff falling onto them and the environments around them can be quite different between the center of a galaxy where the supermassive black holes live, and then stellar mass black holes. If we see them, that's because they're eating a companion star in a binary system. But we see a lot of the same thing. We see jets, we see winds, we see bursts of activity. And in fact, one of the things I've been busy with for part of my career is trying to map the physics from little black holes to big black holes and vice versa. So that's cool stuff.
Yeah, very cool.
But nothing, but again, the EHT is important for that because it helps us to anchor our models for how these episodes happen.
Yeah, even though you cannot see the smaller ones yet.
Yeah. Well, we can see them, but we can't image them.
You can image them, yeah.
Yeah, we see them in other ways.
Yeah, because I guess in the past we would see gravitational lensing, I guess, as a
Well,
as a
yeah,
form to
I mean, the point is we
picture a
know
black
they're
hole.
there from the dynamics, right? We can see, first of all, we see their light coming out in other frequencies, and they have certain characteristics that we've come to recognize as black hole characteristics. But secondly, when they're in orbit with another star, it's just Newtonian orbits, right? If we know the mass of that star and we can watch the orbit wobble, we can actually weigh how much the dark mass is. And if it's over a few solar masses, then it has to be a black hole.
Oh yeah, exactly. So what's next for this? You're saying you're doing a new picture every year?
Well, I don't think it's like on a schedule like per year, right?
Okay.
We're just when we finish, right? So we're going to try now to focus on Sagittarius A star. There's one of the other sources that was not a horizon source, but one of the other black holes we looked at. There's a paper in the works now from the image of that should come out pretty soon, I think. Then there's the other sources we looked at. Then there's the multi-wavelength papers. Then there's 2018 data, which we haven't even gotten to.
So we're going to have a lot of
And
more
then-
similar pictures.
Yeah, but
in
maybe not
circulation.
similar. Maybe they're going to be quite different.
yeah,
We don't
yeah.
really know
Yeah.
what
Of
Sag
course.
Star is going to look like. And then variability, movies, trying to put this all together with other instruments, other facilities.
Beef up the resolution.
And then maybe, we've added more telescopes to the array since 2017, so we'll see what improvements we have. And then maybe going to space.
Yeah,
Yeah.
to study them.
No shortage of plans.
No, exactly. But it also sounds like it's well, maybe it's not a golden age yet, but it seems like you have these new technologies available now that you didn't have before. That makes it possible for you to study all these gigantic dense
it's a
objects.
golden age for gravity, right? When you
Yeah,
think about it, it's only the last 4 years, right,
4.
that we saw gravitational waves in 2015. So it's just been insane.
Yeah.
It's the comeback of gravity.
It's
eh?
really,
comeback of
yeah.
gravity.
I don't know if it went away, but
Gravity never really went away.
yeah.
It's all back in fashion now.
Yeah.
But it's really, I think it is a revolution. And as we start to really be able to combine, I think the holy grail in some sense now is combining gravitational waves with particle signals, so neutrinos and cosmic rays and light, like getting everything to come together. That's what we call that multi-messenger, but that's really where the field is going to a lot of.
And will it help? The more we understand of all of this, I guess, the more we start moving towards finding a solution for gravity and the quantum world not matching with each other, right?
Yeah, I mean, that's the hope, right?
Yeah.
I think that would be really interesting. There's a lot of ideas out there. Some of the more interesting ideas about alternate theories other than general relativity involve different shapes of the metric around the black hole. So we maybe could probe that with better precision telescopes with EHT. There's ideas about almost like vibrational modes of the event horizon. Maybe if you can I find that probably, the problem is, there's a lot of ideas about what you might see, but they're all underneath the threshold of astrophysical facilities.
Mm-hmm.
So,
well, you proved that technologically it's possible to raise the bar.
Exactly.
Yeah.
And so I think the question now is, how good does it have to be able to test some of these ideas? And people are definitely thinking about it. There are actually already people are simulating, for instance, there's still some people who say, okay, maybe this isn't a black hole. Maybe this is a gravastar or a boson star, right?
We need to do a new show. What is it? What is a gravastar or a boson?
I forget what a gravastar is. It's something else, but a boson star is basically, I mean, it sounds pretty weird. Bosons are just other kinds of particles. It's basically a big
BOSON.
Yeah, it's just
right?
basically a kind of a big particle field
yeah.
that can mask itself and conglomerate and look like a black hole in a lot of ways. And you think, well, that's kind of crazy, but then so is a black hole. So I don't know. I mean, neutron stars are totally bizarre. White dwarfs are pretty weird.
The fact that it's crazy doesn't prove that it can exist.
So, when you think firsthand, like, this is crazy, I mean, the fact is, like, there's no reason it couldn't be there. I think there are some problems with these models. But anyway, but people are actually taking the same kinds of computer simulations and showing that, for instance, in some ways, they can look a lot like the black hole when you throw material onto them. And I think in many ways they probably won't, right? Yeah. So then you can start to rule out certain kinds of scenarios. Yeah.
And you're going to try and poke these objects to see if you can figure out what they're actually doing, what they're poking. I mean, you're looking at them. Mm-hmm. But it seems that something that was such a mystery 40 years ago, 30 years ago, is now layer by layer, you're actually seeing, at least you're starting to know where to look.
I think, when you think, again, like, it was just 100 years ago that we started to understand that we don't live in this Cartesian universe, right? That the universe is actually made of many dimensions and that we experience 3 dimensions of space, but the 4th dimension, time. And then if you think about string theory, there's other dimensions, like 11 actually, and so we don't experience those on a physical level, but they turn out to be important mathematically if you believe those theories. And where does it all come from? We don't understand where gravity comes from exactly, but I think it's crazy that we're like, we crawled out of the mud and we were like fighting wars for most of the last, I don't know, you think about human history, it was pretty primitive for a long time. And then in 100 years, we get this far. It's pretty cool.
That's a great way to end the show.
No, it's not. Because I have one...
go for it.
Perhaps last question. Who's getting the Nobel Prize now?
Oh, yeah.
Who's getting the Nobel Prize?
Well, I don't really know if this, that's a question, right? I think there's...
I've written down a couple names,
There's 200 people.
Well, that's
involved.
the thing. I have to say, personally, I hate the whole idea of that because there's a real issue. I frankly think that giving a prize to a couple people is against the entire spirit of the collaboration.
Maximum 3 in the case of a Nobel Prize,
And 3 people, of course, there's way more than 3 people who are fundamental to gravitational waves or to this project. And I think that what it does is it creates an unhealthy dynamic. And I think it creates a pressure that doesn't need to be there. Mm-hmm. So I'm actually really not interested. But I think, my feeling is that maybe this is too close to gravitational waves. I don't know that it would be considered close enough that it's not going to get a Nobel Prize because it's in the same vein.
Possible.
I don't know.
Yeah.
But I really, I think it's a destructive thing. I much prefer things like the Breakthrough Prize where the entire collaboration gets awarded, right? Or, where that's recognized. It's a nicer thing.
I think the Nobel Peace Prize over the past
Organizations sometimes
Yeah.
get
organizations
them.
or ideas or
Right. So I think
That
a
would
lot
be
of
a
us
fine
would
idea.
rather see that the Nobel kind of modernizes into recognizing that these are collaborative efforts. Because as you all saw with the media, there was this need to create a narrative of the lone wolf or the hero
Yeah.
or the victim.
Yeah,
yeah.
That I
The
saw
driving force
The
or
driving
whatnot,
force. And
yeah.
there's a lot of different people who contributed very fundamentally. And this really was a team effort. And I kind of just wish... isn't it kind of a nice story for the era that everybody's getting along and working across borders and we managed to do this thing? And science is the hope of humanity, right? In that sense. And
Selma said the same thing. Selma the Mink.
Oh, yeah, Selma,
your colleague that we had
yeah.
on earlier. It's the same thing. I believe I said something about a person standing up and yelling "Eureka!" And she's like,
Yeah.
"No,
Yeah.
no, that's
We're
not
not doing
how
that
science
anymore."
works." Yes, I got schooled.
Yeah, but I think it's also destructive in how it gives this perception of kids. Kids get turned off to the idea of doing science because there's this myth or this persona that they see. They think that you have to be some kind of loner sitting in a dark
But don't you think that
room.
can inspire as well?
I don't know. I don't really think so. Think about social media. Obviously, people feel the need to feel connected all the time now, and so if you tell people who maybe even more than in the past need to feel connected constantly, like our youth today, that the idea that they might have to work in isolation, which isn't true anyway, but if they have that perception, I could see why that would turn them off to science, where of course it's extremely collaborative and
But sometimes it helps to have heroes, doesn't it?
I don't know. I know that it does in certain narratives.
Yeah.
Right? But I feel like it's been almost more destructive lately for science to keep trying to heroize individuals when you have these teams.
Because you get fights and who got left out.
Yeah,
And
exactly. And it
everything,
creates other narratives that are maybe not so healthy for the collaboration.
Yeah,
so
that's true.
I personally think, at least when it comes to science, it's maybe nice to think about, there's people who came up with great things and we should celebrate them. But usually these things don't happen in isolation. Einstein was building on the work of other people and, in fact, incorporating the work of people he was in almost daily contact with. He didn't come up, the Schwarzschild radius didn't come from Einstein, that came from Schwarzschild.
Sure.
So
Yeah.
people talk to each other.
Okay.
Yeah.
You just made me decide on the spot not to read aloud the list of names that I have.
Exactly.
I wouldn't do that game.
Yeah,
No.
we would
Okay,
also
fine,
rehash
very
like a whole
fine.
bunch of controversy on that happened on the internet after this whole thing.
Yeah,
that
and
thought was
I really
incredibly
found
annoying.
I found a lot of that controversy just totally made up.
Yeah, totally made up.
Yeah.
So let's not do that here. Yes, we're making a statement by not reading your list.
Thank you.
That's right.
Hey, Sarah,
happy.
thank you so much for being here and
Thank you.
and explaining this all. And
I hope it wasn't too technical because some of it was getting a little technical.
yeah, but
there.
that's what I love about
That's all right.
being able to do this show is that and so also for the people listening, you get more than an hour to talk about this.
Yeah, it's nice,
just so
actually.
that we can do those things and we don't have to.
Exactly.
Yeah, I mean, there's always people listening who understood every word you said, and some people don't.
Yeah, hopefully, and they're probably saying she said it wrong.
Yeah, exactly. We'll correct it, then we'll have a new conversation.
Or some people decide, hey, let's Google that.
Yeah, exactly. Yeah, I saw a Dutch host once, Matthijs van Nieuwkerk, famous host. He said in every conversation you sometimes have to, mention a few things that people don't understand, so that you at least have something to aspire to still. So it's, but who knows? I love this all. So thank you very
Thanks a
much,
lot.
Sarah.
Thank you.
Yep.
Yeah, and thank you, Herbert.
Thank you, Thijs.
Thank you to all the listeners as well. And quickly, next week, do you know?
No, not by heart. We're going to talk with our dear friend and colleague Yuri
Oh, Yuri is there next week.
from BNR.
Yeah, so
He's
next
going
week,
to tell us all about all the upcoming space events.
Yeah, so
like
it's gonna be-
launches and everything.
after all these conversations that we had with wonderful scientists about all these amazing findings, we're now just going to do updates about what's happening, what's
getting
going on.
launched
Yeah, what's
when,
going because we
and
missed a
what
whole
for.
bunch. Yeah, we missed so much already. So that's
Yep.
up next week.
So Yuri is back after 2 months of absence.
Exactly. Thank you all.
Thanks. Bye-bye.
Bye.
Bye. Thanks.